In this video, we're going to see bipolar junction transistor under equilibrium. Bipolar junction transistor in short form is called as BJT. Three gentlemen, namely William B. Shockley, Walter H. Brattain, and John Bardeen, received Nobel Prize in the year 1956 for their invention of BJT in 1947. Since its invention, for nearly 3 decades, it was the device of choice in the design of discrete and integrated circuits. It has been used extensively in high-speed circuits, analog circuits, and power applications. Later, use of BJT has declined in favor of CMOS technology. But still, even today, in specific applications like bandgap and electrostatic discharge circuits, BJT is used. It is a bipolar device because both polarity of mobile charge carriers, electrons and holes, participate in the conduction process. Transistor name comes from transfer resistor, and BJT is a bijunction device. So we have two PN junctions. We can form two PN junction device like this, where this is P-type material and this is N-type material, and this is again P-type material. We have one junction formed between this P and this N, and another junction formed between this N and P materials. So basically we have two junctions. Similarly, we can have N material, P and N material. We have one junction here and second junction here. We call this as emitter, this as base, and this as collector. We'll understand this nomenclature in detail once we understand the operation of this transistor. And similarly here, this is emitter, base, and this is collector. And we have three terminals to it. First terminal is emitter terminal, second base terminal, and third collector terminal. And similarly here, as we have two PN junctions, one between emitter and base and the other one collector and base, so we call this junction as JE, representing emitter junction, and this one as collector junction. And of course base is common for both, so we are not explicitly specifying it here. Similarly here as well. If you take doping on emitter is N suffix E and doping on base is N suffix B, and similarly doping on collector is N suffix C, usually emitter is heavily doped compared to base or collector. So in general we represent this as P plus, and similarly emitter doping on this also would be high, so N plus. So we have two types of BJTs, one Pnp transistor, other one NPN transistor. That's how we are going to call them. And here the relationship between these would be in such a way that emitter doping would be always greater than base doping, and most of the case it will be really high, and we will see the reasons why it is. And collector doping would be less than base doping. And in fact, sometimes people call BJT as a triode because it has three terminals. And now to understand BJT under equilibrium, let us pick one out of these two and understand them so that for the other one you can do analysis yourself. So for that, I'm picking Pnp transistor to start with. So first let me draw the doping profile represented by Nd minus Na. We know emitter is P-type, so Nd is 0 and Na is a very high value. So Nd minus Na would be a negative value. So let's take this is minus Ne representing the emitter doping. I'm assuming emitter, base, and collector are uniformly doped. So this quantity would be N suffix E. And on base side, it is N-type doped, so Nd will be a finite value and Na would be 0. So Nd minus Na would be positive. So I'm representing that here, where this value would be N suffix B. And on collector side, N suffix C magnitude would be less than N suffix B. So I'm taking it to be somewhere here, where this value is N suffix C. If you see here, the doping profile is changing abruptly at the junctions. Emitter to base there is abrupt change of doping, and base to collector there is abrupt change. As we are assuming this BJT is in equilibrium, which means there is no net current flowing through it. So equivalently, we can assume that all terminals are grounded. Now let us look at the volume charge density inside the Pnp transistor. We know for a PN junction, at the junction there would be depletion width, and there would be electric field, and there would be potential as well. And we have seen this in the p-n junction. So I'm taking directly that on p plus side, the depletion width would be small, n side would be more. This is the depletion region on p side, where the exposed ions would be negative in nature. And this is in the base. The depletion width would be more, but the area of this one and this one would be equal. This would be Q times NB, and this would be minus Q times NE. And on base to collector junction, on base the depletion width would be something like this, where the magnitude would be Q times NB, but on collector, to have the same area, the depletion width would be more, and this would be minus Q times NC. Depletion charge in n-type material would be positive, and depletion charge on p-side material would be negative. And we are taking this is the width of the emitter, and this is width of base, and this would be the width of collector. Now once we know the uncompensated charge distribution, we can find the electric field inside these junctions, and let us plot them. Now I'm taking electric field on y-axis and distance on x-axis. Once we know charge distribution, we can find electric field based on this relationship, which we have seen while understanding p-n junction diode. So I'm integrating rho v over epsilon from left side to right side. Till we reach this point, the area would be 0. So till that point, electric field is 0. And as we move in positive x from this point, the area would be negative. So the electric field would be negative and in this direction. As we cross this point, to this negative value, a positive value gets added. So it becomes like this. And as this area is equal to this area, electric field at this point would become 0. And this width would be the depletion width at the emitter junction. And now once we cross this point, till this point the area would be 0. So after this it would be positive. So we are adding positive value. And as we go forward, a negative value gets added. So this electric field decreases, and once we reach this point, it would be 0. Because this area would be equal to this area. And this width would be equal to the depletion width of the collector junction. Here electric field is negative, indicating that electric field is in minus x direction. That is very clear because this is positive charge, this is negative charge. Electric field would be from positive charge to negative charge. And here electric field is positive, which means electric field is in positive x direction, which indicates from positive charge to negative charge electric field is directed. Once we know electric field inside BJT, we can find potential distribution, which is given by minus integral electric field times dx. So let me take potential on y-axis, distance on x-axis. If we integrate left side to right side, till this point the area would be 0. So potential till this point is 0. It would start from this point, increase, and it stays constant till it reaches this point. After that, as we have minus of this plus would become minus, so it starts decreasing. And it goes on till this point, and then it becomes straight, and it wouldn't change. And if we recollect, this value would be nothing but the built-in potential. And of course, this would be built-in potential for the emitter junction. So remember, this is for emitter junction, and this value would be the built-in potential for the collector junction. We know pretty well the built-in potential is actually given by Vt times ln of Nd Na over Ni square, where Nd and Na are dopings on either side of the junction. So if you see, Nd and Na values are pretty high for emitter base junction compared to base collector junction. As a result, the built-in potential for the emitter junction would be high compared to collector junction. That's why we have shown the graphs like this. Let me first rearrange these graphs before we draw the last diagram, which is energy band diagram. As we assumed, this BJT is under equilibrium where there is no net current flowing through this Pnp transistor. So the Fermi energy level should be constant throughout this transistor, and it should not be changing with respect to distance. And that's why EF is shown constant throughout this device. And this is EC, this is EV, and the difference between EC and EV is EG. Emitter side, EF should be very close to EV because emitter is p-type, heavily doped, so EF to EV would be very small. And coming to base, it is n-type, so EF should be close to EC, and that's what is shown here. And this magnitude of difference EC to EF should be greater than EF to EV with respect to emitter, because emitter is heavily doped compared to base. Coming to collector side, EF should be close to EV compared to EC, and that's what is shown here. The difference EF to EV at collector side should be greater than EC to EF at base side, because base is highly doped compared to collector. And we can also represent the total band bending at the emitter junction is Q times VBI of emitter junction. And similarly, we can say the overall band bending on collector junction is equal to Q times VBI of collector junction. And we know that VBI of JC is less than VBI of JE. And this band bending basically represents that there is electric field in this region. And that's why it is actually a dotted line to represent that there is a depletion region at the junction, which is negative on P side and positive on N side. And similarly here, positive on N side and negative on P side. As there is depletion region, there is electric field. As electric field is present, the band is bending. And the band bending actually represents that electric field is present. So even here, the collector junction's depletion width is higher compared to the emitter junction's depletion width. As you can see, the dopings on emitter junction is high. As a result, depletion width would be small. And on collector junction, the dopings are less compared to emitter junction. As a result, depletion width would be higher. But from now onwards, in next videos, we'll not be drawing all the plots. We'll draw only this figure and the energy band diagram.